In this video, we're going to be looking at a complex locus problem, where we're looking at the argument of z minus 2 minus the argument of z plus 2 is equal to pi on 4. Now, this is one of the more difficult complex locus problems. And the reason that this is difficult is because it sort of joins a few things together, and we'll see that as we do the problem. Now, a lot of students seem to just memorize what this is going to look like and then just apply it. But I feel that really lacks a conceptual understanding of the problem. And I hope this video is able to shed some light on why this forms the shape that it forms and how we get to it. Okay, so before we start considering arg of z minus 2 and arg of z plus 2, it's a good idea to think about, well, what does arg of z mean? Just arg z. And what that is we have a half line or array which emanates from our origin. So what I'm going to do is I'm going to put a thumbtack. What I've got here is just a straw with a thumbtack at the end. And I'm going to place that at the origin. Push that in a little bit. And then this is arg of z. Z is all the points lying on this line. Arg of z is going to be that angle there. So the angle that this half ray or this half line forms with the positive real axis is known as arg of z. But we don't want arg of z. We want arg of z minus 2 and arg of z plus 2. Well, arg of z minus 2 is the ray or the half line that emanates from the point 2. So instead of starting at the origin, we're going to start at the point 2. And then this angle, let's get a pen. This angle here is the angle arg of z minus 2. Hopefully you can see that. And then what's the other one? Well, the other one is arg of z plus 2, and that's going to be emanating from the point 2. Sorry, from the point negative 2. Let's push that in. So this here is our ray, and arg of z plus 2 is going to be this angle in here. Arg of z plus 2. Okay? So that's what we're really talking about when we talk about arg of z minus 2 and arg of z plus 2. Now, how do we relate these two angles to each other? Well, if I had moved this so that they overlapped, and actually they would overlap if my straw was longer, but if I just move it so that they do overlap, well, this angle here is arg of z minus 2, and this angle here is arg of z plus 2. And we can relate these because they're both related to the same triangle. If you can see, there's a triangle being formed here. And arg of z minus 2 is the exterior angle, and we know that the exterior angle of a triangle should be equal to the sum of the two interior ones. So let's write that. Let's get a red pen, and let's see if we can fit it here. The arg of z plus 2, which is that angle there, if we call this angle between the two rays, let's just call that theta. Okay? So this arg z plus 2 plus this angle theta should be equal to the exterior angle, which is arg of z minus 2. And then if we just rearrange a little bit, we can get arg of z minus 2 minus arg of z plus 2. Unfortunately, I've gone over that there, but hopefully you can see that's arg of z plus 2. That's equal to our angle theta. So theta in here is this angle minus that angle. But according to our question, we want theta to always be equal to pi on 4. Okay, that's the same as arg of z minus 2 minus arg of z plus 2. Okay, and our question is asking, well, when is that always equal to pi on 4? When is theta always equal to pi on 4? Okay, so that's what we really need to look for in this problem. So let's get a new argand diagram and start looking at this. Okay, so now we have a fresh argand diagram. And what we're going to do, I've actually substituted out our rays for some strings because I think it's a bit more practical with the string. This is actually an activity that I would do in pairs if I was teaching in a classroom. However, since I'm by myself, I'm just going to try to do it as best as I can with one pair of hands. So I would get one of the students to be holding the strings straight, and then the other student would have a cutout of a triangle which has a 45-degree angle right here. And that's going to be used to measure the angle between these two rays. So what the students need to do is they need to move these rays so that they are exactly 45 degrees apart. So one student moves the rays and keeps them straight, the other student measures. Now, this is going to be a little bit difficult by myself, but I have actually cheated and put in some marks for myself. So I think that this point here will be about 45 degrees. And if I check, there you go, that's about 45 degrees. So with one of the students holding this tightly, you remove that, get your pen, and just make a little mark here. And then you keep going around and you do the same thing. And I've actually done this in my own time. Don't know if you can see them, but there's some little marks here. So it's a little bit off there, and so on. There's a few marks around the place. Okay, and that's something that students would do. And they would try to go all the way to the extremities as well, down to here as well. Okay, and what they will find, and what you should find, is that this is going to form a circle. However, it's not a complete circle, because once we go below the real axis, our angle isn't going to be pi on 4. That's not going to fit below the real axis anymore. So let's remove these, and let's try to actually draw this circle. And it's not very easy to do freehand, but I'll give it my best. Okay, it's something like that. Now let's go back to what the question was. I didn't actually write it down here, but the question was the arg of z minus 2 minus the arg of z plus 2 is equal to pi on 4. Now hopefully you're watching this video with a bit of knowledge about args, and you should know that we can never have the arg of 0. So that means z can't be equal to 2 and z can't be equal to negative 2, because they would make both of the insides of these args become 0, and that's something that we can't have. So that means we need to actually exclude these points here. So we put an open circle. Let's move it up. We put an open circle, okay? So let's just go over that again. That the idea behind this is that any point on this circle, if I drew a line like this and a line like that, the angle between these two will always be pi on 4. So let's take a very particular case. Let's have a look at this point here. Okay, and I'm choosing this point because it's exactly halfway between 2 and negative 2. So, and in fact, now that I think about it, I don't even need to choose this point, but it's always a good one to choose. Any point on the circle is going to actually help my argument. So, we know that this angle here is pi on 4. Now, if you look very carefully, unfortunately, this is something that's not taught in Extension 1 maths anymore, because they took circle geometry out of the syllabus. But you might have seen this in Year 10 in stage 5.3. There is a circle geometry theorem which relates the angle at the circumference to the angle at the center of a circle. And that says that the angle at the circumference is half the angle at the center, or the angle at the center is twice the angle at the circumference. So if we choose this point to be the center, and I'm placing it there just because I already know it's going to be there, but this angle that's here, this angle at the center, is going to be twice the angle at the circumference on the same arc. And these are on the same arc. So this angle here would be twice pi on 4, which is pi on 2. So this is actually a right angle. And the reason that we do that is because that's going to help us, firstly, it's going to help us find the center, and it's also going to help us find the radius. You can see that this is the center, and it's going to the edge, so that's the radius. All right, so how do we do this? Well, let's think about taking this triangle, this one here. Let's just take that sort of out of the diagram and look at it separately. So there's one here, That's this line. And then we have the base, and then this bit here, which remember is the radius. So I'm going to straight away write r here, just so I don't forget that that's the radius. Obviously, this angle in here is a right angle. And this angle here, well, what's this angle going to be? This is going to be half of 90, okay? Because this is an isosceles triangle, and this angle here is going to be bisected. So this is going to be pi on 4, which means that this is also pi on 4. So actually, this is also an isosceles triangle. And I know the length of this, that's from 0 to 2, so this side length is 2, which means that this side length is 2. And then we can use Pythagoras' theorem, and we would find out that this is 2 root 2. So I found that the radius of my point, of my circle, is 2 root 2. What's the center? Well, the center is 2 units up from the origin, and so that's going to be at the point 2i, or 0 plus 2i. So let's write that on the side here. We have a circle, but it's not actually a circle, it's really the major axis. Sorry, major arc, not axis, major arc. Our center is at the point 0 plus 2i, and our radius is equal to 2 root 2 units. Okay, and that, if we did it like this, that's everything that we need to show. All the critical features about this locus here have now been shown. There is another way that we can work out the center and the radius of this, and it's a purely algebraic method. Let's have a look at that. This is our question again. So we have arg of z minus 2 minus the arg of z plus 2. Now there is a nice identity about args that hopefully you should know, which sort of, they act similar to logarithms, and it's no coincidence that that is the case. But we won't talk about that. We'll just apply that property, that arg of something minus arg of something is arg of z minus 2, in this case, over z plus 2. Right? And that looks very similar to what you see with logarithms. Again, that's not a coincidence, but it's sort of a bit out of the scope of the course. So what's this saying? This is saying that the arg of some complex number, this is just some complex number, is equal to pi on 4. Okay, well, what does that mean? This is our argand diagram here, and we have a complex number z. This angle is pi on 4. Okay, now the line, if we were thinking about this on a Cartesian, in terms of Cartesian coordinates, this line here would be y equals x, because it has to have a gradient of 1. So if this has a gradient of 1, that means the rise over the run is equal to 1. All right, let's write that again. The rise over the run is equal to 1. But what is the rise of any complex number here? Well, it's just the imaginary part of this thing. And what's the run? It's just the real part of this complex number. So this is saying that the imaginary part of z minus 2 over z plus 2 over the real part of z minus 2 over z plus 2 should be equal to 1. Let's multiply through by the denominator. Give us real of z minus 2 over z plus 2. Now, before dealing with this, let's actually just have a look at what z minus 2 over z plus 2 is. Let's get a different color. Z minus 2 over z plus 2. If we can actually work out what this is and write it in terms of a plus ib, we'd be able to pull out the imaginary part and pull out the real part, which is exactly what we need here. So, well, z is x plus iy, so let's sub that in. X plus iy minus 2 over x plus iy minus 2. Let's collect the real and imaginary parts in the numerator and the denominator. We get x minus 2 plus iy over x, sorry, that should be a plus, x plus 2 plus iy. And now we want to realize the denominator. realizing the denominator. So that means we're going to multiply the top and the bottom by the conjugates of the denominator. Okay, hopefully you know why we're doing that. So x minus 2 plus iy is multiplied by x plus 2 minus iy. And if you don't know why, you're about to see why we multiply by the conjugate. All right, so this is all over x plus 2 plus iy times x plus 2 minus iy. So in the denominator, what we have is we have a difference of two squares popping up. However, because we have an I squared here, that becomes a positive one. So we're going to have minus I squared, and minus I squared is the same as plus 1. So this becomes actually what's known as a sum of squares. So it's a little bit different when we're dealing with complex numbers. But anyway, let's deal with the top. We have x minus 2 into x plus 2. Let's go iy times x plus 2, it gives us iy x plus 2. Then x minus 2 minus iy. And then minus iy, iy times minus iy is going to be minus I squared y. Let's just do it all in one step. Let's do it in multiple steps, I should say. Then we have x plus 2 times x plus 2, so that's x plus 2 squared. Iy times minus iy, which again is minus I squared y. All right, now let's tidy everything up. So you can see that difference of two squares is now going to become a sum of two squares, because this minus I squared is really just plus 1. Expanding that gives us x squared minus 4 plus iyx plus iy2 or i2y minus iyx, and we can see straight away that these are going to cancel. Minus iy times negative 2 is going to be plus i2y, and then we have plus y squared here. All of that over x plus 2 squared, forgot a squared here for that, plus y squared. Okay, now let's collect all the real and imaginary parts together. So all the real parts on top, where are they? We have x squared. We have, so I'm going to cross that off. I'm going to cross it in that direction because I've used it, y squared. And then we also have minus 4. So that's a real part, and that's being divided by this, x plus 2 squared plus y squared. Probably can't see that. And then what else? What's our imaginary part? Well, our imaginary part is minus or positive 2 iy plus positive 2 iy. So that's 4 iy over the same denominator. Beautiful. So now we have z minus 2 over z plus 2 in terms of a plus ib. So what did we want to do with that? We wanted to equate the real and imaginary parts. So that means that we have x squared plus y squared minus 4 over x plus 2 all squared plus y squared equals 4y over x plus 2 squared plus y squared. Now we have the same denominator on both sides, so let's multiply through by that. However, when we do that, we need to be a bit careful because we need to make sure that we restrict our domain. So let's just write it and then we'll see what I mean. So we multiplied through by x plus 2 all squared plus y squared. But at this step, we need to note that x comma y cannot be equal to negative 2 comma 0 because that would make our denominator 0. And so we have to also do the same here. X minus y cannot equal negative 2 comma 0. And then x squared plus y squared minus 4y is equal to positive 4. I'm going to try to fit this on the one page. I'm going to complete the square here In doing so, that'll give x squared plus, let's see, y minus 2 squared equals 8. So I added 4 to both sides to complete the square. I did that bit a little bit quickly. But this is the equation of our circle. Okay, now and we can see that 8 is the same as 2 root 2 squared. So you can see the center is at 0, 2, or 0 plus 2i, and our radius is 2 root 2. The only disadvantage that this has is that it's not actually completely correct, because this is saying that it's the entire circle, when we know from our geometric approach that it's only the top major arc. It's not the entire circle. So you need to be a little bit careful when using the algebraic method, although it does give you the correct center and radius of your circle. So if a question was just asking for the equation or the center and the radius, this is a perfectly fine method of using.